So my talk is about Scala, the road ahead, and that's what I'm going to talk about. It's great to be back in Berlin after, I think, a 2-year hiatus. I can tell exactly because we're always coming to Berlin when there's a World Championship or European Championship. Last time I gave the talk, it was actually right before the first game of the German team, first game in the World Championship, and we know how that ended, so that was a very nice experience. We all watched the first game at the reception afterwards. So I don't think there's a German game, so I'm not competing with anyone today, so I have everything for the whole stage for me. Thank you for that. So, Scala, the road ahead. So I'm going to talk a little bit about what's coming up for Scala. First, what has been. The recent past has been, I think, more on the quiet side. There was a steady movement of essentially all the indicators were going upwards quite steadily. So on the left-hand side, you see the jobs of Indeed.com, and people were always laughing to say, well, if you look at Java jobs and Scala, it doesn't even get off the line. So now I'm very glad to say it goes a little bit off the line. So Scala jobs are now about 5% of Java jobs in that index, and I think that's, of course, not the same thing as Java, but it is respectable. The other nice trend is Google Trends, Scala Tutorial, which is quite interesting for its smoothness. So it just goes very smoothly up without big excitements, but steady progress. And I leave it up to you to just relate that to some of the graphs of, let's say, other technologies of languages. And there you see that this is actually quite untypical, that normally it goes up and then it goes down again. But for Scala, it's sort of, I would say we're probably beyond the hype and in the phase of essentially steady adoption. And that's very nice to see. So 2016, things will heat up again. So what is in store and what has already happened are many, many interesting things. The first one is the Scala Center, the new release of Scala 2.12, the next major Scala release. We are starting to rethink Scala libraries. There have been exciting new developments in the target platforms. And finally, last but not least, there has been a lot of new work on dot, the foundation of Scala, and dotty, the experimental compiler to implement that foundation. So I'm going to talk about all of that in the next half an hour, 45 minutes. First, Scala Center, I'm not going to talk about much because Heather actually will give the keynote tomorrow and will explain you all of that in great detail. Just one word, Scala Center's mission is to undertake projects that benefit all of the Scala community. So it's vendor neutral, but it has industrial support from a number of sponsor companies, including Lightband, Goldman Sachs, Nitro, IBM, 47 Degrees, Verizon, Tapad, and we get new interest from more companies essentially every week and every month now. So I expect that list to grow until the end of the year. The other big mission of the Scala Center is the MOOCs, the massive open online courses, which you might have noticed that they have restarted on Coursera. And despite the recent fright, no, they are still free, so you can still do the courses without paying for them. And you can also get the assignments graded without paying for them. But of course, if you want to enroll and get a certificate of the specialization, then there's a fee to pay, and the Scala Center gets, as far as I know, about half of the revenue that, essentially there's a revenue split between Coursera and the Scala Center. So by enrolling in these courses, you also do your bit to actually support the Scala Center here. Scala 2.12, that's the release that's literally around the corner. I think the Scala 2.12 team is very close to do the last milestone, cut the first release candidate. The main new things in Scala 2.12 is that it is optimized for Java 8. So Scala 2.11 could already work. You can run it on Java 8, of course, and I think many of you do. But it didn't really take advantage of the new features in Java 8, which is in particular the lambdas, so essentially the native support for first-class functions, and the default methods. The lambdas, of course, are very good fit for Scala's functions, and default methods are a very good fit for Scala's traits because they give you a much more lightweight encoding of Scala's traits. So Scala 2.12 is the release that actually makes use of these two things, and by consequence, it will require Java 8 because it can't run on an older Java version. So that means that to use 2.12, you need Java 8. And I don't know how many people here are already on Java 8. The majority, I think, but I think there's a sizable minority that's not yet there. And we know that it often takes longer, and so there's a long tail. So for that reason, there's a longer than usual maintenance period for Scala 2.11. So 2.11 will be maintained longer to help those people who actually cannot yet move to Java 8. That also meant that for the language feature releases, the current trend was to be very, very conservative because we didn't want 2.12 and 2.11 to diverge too much because we knew that essentially we had to, or the Scala team knew that they had to maintain them in lockstep for quite a while. So that's why maybe 2.12, except for this really great support for Java 8, is rather on the conservative side on what concerns new features. That said, there's still 33 features in the release notes, so you find it all on GitHub, and the Scala team has done an excellent job in actually stabilizing the whole code base and make really what we all hope is a rock-solid release for 2.12. So here you see the three top committers, Lukas Rietz, Jason Zorc, and Adrian Morse, and there were many, many others, and we are also very happy to say that many of these committers are coming from the community, so they're not Lightbend employees, they are really contributors from EPFL, from outside, from third parties, and so on. Finally, I can say that programming in Scala 3rd edition is out. That took a long time. There was a long time in the making. The last edition we covered, I think, was 2.10. So that edition now actually contains the latest parts that actually cover the 2.12 bits, and there's a book signing on Thursday during lunch, 12:20 to 13:20, at the Lightbend booth, where me and Bill Venners, who's also here, will sign your Programming in Scala 3rd edition books if you give them to us. So those are sort of the things that are almost already out there, so immediate. So I think now is a time to think about, well, what will come afterwards? What are the next steps beyond 2.12? The next step beyond 2.12 is 2.13, of course. And for that language version, we decided to focus more on the libraries. So where 2.12 was essentially a version that was more the compiler internals, compiler optimization, compiler code generation parts. 2.13 will be more user visible because it will be will focus on the libraries. In particular, we plan to have a second look at the Scala collections to make them, where we can, even more simple to use, where we can bring them more in line with Spark usage, maybe by making it easier and more robust to use lazy collections and to maybe add some of the features that you find in Spark and that you don't find in standard Scala collections, like the nice support for pairs, collections over pairs and pair RDDs and things like that. That said, we definitely want to remain largely backwards compatible. So for a normal user of collections, like if you don't do fancy stuffs like implement your own collections, frameworks, and things like that, nothing should change. So it should just essentially become a little bit more streamlined and simpler. The current status is that we have some strawman proposals under study. That means what we tried to do was to say, well, let's study the architecture in something that can be done in reasonable time and space. So currently the line limit of these strawman proposals is 500 lines. So we want to essentially capture the essence of what we try to achieve in something like 500 lines and have several of them so that we can compare them and essentially then decide what a good architecture for going forward would be. The other thing we are considering and thinking about is to remodularize a little bit the Scala standard library. So Scala standard library is something that has grown historically, and the way it has grown historically, that essentially there was this explosion phase in the very, very early years, probably before most of you got involved in Scala. That was like 2005, 6, 7 around, when essentially we took every module that somebody would contribute to say, yeah, great, we need that, we have nothing, so let's just put it all in. And then I guess nobody realized that these things would stay with us forever. Or at the time, we didn't even realize that the language would stay with us for that long, so you don't really plan ahead for these things. So that's inevitable, that's just how things grew, but the question is, can we now get some improvements by maybe better modularization? Can we distill the core of this library where we say, well, we're really happy with that, and that should be sort of part of every Scala compiler's toolbox, and maybe have modules for parts that maybe are more optional and that wouldn't be part of what everyone wants to use. And in particular, one idea that has been floated is to actually have a Scala core library, which is sort of what everybody agrees, and then have to something which is probably much larger than the current library, call it the Scala platform, Scala batteries included, that essentially would have state-of-the-art solutions for a lot of the application areas that people want to use modules in. I think that would be, personally, I think that would be a very, very good development, but it's something that I can't do myself, and essentially the core teams can't do themselves. So if that should happen, then it would involve you, the community. It would need a lot of people to get involved and say, well, let's get together and make this happen. So that's something that hopefully we can plant the seeds, but then to a large degree, we will have to rely on you. New platforms, so there's Scala JS 069 out. It's a steady progress of the Scala JS releases. In the latest one, we have native anonymous classes, support for tuples, JUnit, support for JUnits, and much faster code generation. And the other thing, that sort of dark horse in the platform, is Scala Native, which is a very, very young project still, but it made the day it was announced that the Scala Days New York, I think it made the top of the Hacker News list and stayed there for a while. So obviously we were quite overwhelmed by enormous interest. So I think nobody could have foreseen that the interest would be so strong. And I think now the question is just how to follow up on that and really get something out. But I think it's very, very promising, and we are looking forward to what the current status is. And again, Dennis Shabalin, he will tell you more about this later on in the conference. I should say also for Scala JS, of course, Sebastian Duran, he will also give you the latest, and I think he will give you at the conference sort of the inside story, how the Scala JS compiler works internally to get the very, very impressive speed that you get out of Scala on the JS platform. So what essentially the secret sauce that the compiler uses to make it all happen. So that's the two talks about the platform that you will get later in the conference. And then there's the dot. So the dot is the foundation of Scala. It's an acronym for dependent object types. It's a little calculus, so that means sort of a mini language, a tiny language that can sort of fit on a page in the definition. And the reason for doing that is that it should be small enough that we can make formal statements about what it is, what properties it has, and that we can prove these statements. And the current gold standard in proving these statements is actually prove them mechanically. That means the proof itself is a program that gets checked by a computer. The proof happens to be written in COC, which is essentially an automatic proof system. But essentially, you want to essentially get to a point where you can establish these properties and be 100% sure that they hold. The other reason for picking a new calculus is, and not something standard like lambda calculus, is that we want to encode much of the rest of the language in it. We want to be sure that what we prove here actually relates to Scala, the language, and not essentially to something that's completely different from it. So the calculus was chosen to be sort of an essence of what Scala is and what the core of Scala is. So that thing concludes an 8-year effort. So we have been trying to get there for 8 years, where essentially we were studying these calculi and trying to prove the core theorem, which is type soundness. And that took us, like I said, an enormous amount of time, and we're very, very glad that we finally succeeded, and we learned a lot over those 8 years. So it wasn't that it was wasted time, but there was really a lot of techniques and a lot of concepts and ideas to learn. So now that it's done, it opens the door to do language work with much better confidence than before, where before we essentially were unsure whether this thing is sound, this thing is correct. Now we actually have something that we can put these things to the test. So this should help us a lot going forward. So I just wanted to give you a quick rundown of what this dot thing is, just to give you an idea what these academics are up to in their ivory towers. So if you translate it to Scala notation, the actual publication uses a lot more Greek than that. But translated to Scala notation, the language by dot is essentially this thing. You have values, so you have essentially these anonymous functions, those are values. And then you have these anonymous objects, so that thing is a self-type, that thing is some definitions that are values. So functions and values, okay, that looks pretty much like Scala. Definitions are just parameterless methods. We don't need more because the rest we can do with lambdas, right? And type definitions, so type definitions sort of are an extract of what we would use to also define classes and traits. And then the terms are essentially a value, like these things are terms, so that's the expressions you can write. Variables are expressions, function application is an expression, the dot, so selection is an expression, and then you have blocks and local definitions, and that's it. So you could say, well, that really looks pretty small, but it's also something which turns out that we can actually encode the essential concepts of Scala in it. The types of dot, so we also have to do them. So we have the familiar any and nothing. We have type selection. We have function types. So we have then essentially structural types, which is just a single definition or a single type definition. Then we have intersection, that used to be called with, so I'm getting to that. And finally, we have recursion, which is not primitive in the language, which is sort of indirectly you can define that by using these refinement types. So that's what the formal system is about. And what have we shown about it? Well, simply this, that we say, well, if a term, an expression, has a type t, and the evaluation of t by the computer terminates, so you get a result, and the result will be a value of the same type t. So a value means it will be something that is actually a usable result, one of these things here. It won't be some weird things like a crash or something like that. And furthermore, it tells you that types don't lie, that essentially the final result of the program has the type that the type checker and the compiler has computed for this. And that result took us 8 years to establish with many, many iterations. So why is this important? Well, I think it's important because it gives us a technique to reason about the correctness of other language features. And some of the examples we've already seen, for instance, we could see that one of the core features of Scala projection, the hash thing, is in general unsound. So, well, it's actually not that much of a core feature. It's used in some of the essentially computations that lift computation to the type level. But fortunately, there are other ways to do that. So it showed that this is sort of irredeemably unsound, and there's nothing we can do about it, and we should drop the feature if we want to have a sound language. And the fact that essentially we knew about the proof principles now that we have dot, and we can project this into the language helps us a lot. By contrast, it also gives us much more confidence with other things that might be much more advanced to say, well, this thing is sound, and we know that we can do this in good confidence. So it gives us essentially a rote Faden, a guideline where to go with the language design. Now the practical instantiation of this language design is dotty. So dotty comes from dot, so it's the working name for our new Scala compiler. Dotty builds on dot in its internal data structures. So what you've seen in the calculus is very much what you would find in the compiler as well, basically one-to-one in the types. It actually does this encoding quite literally. For instance, in the Scala, the language, of course, you have generics, you have type parameters. Type parameters are everywhere. You have type parameters of classes, of traits, of abstract types, and things like that. In dotty, most of these type parameters get actually expressed as type members. So essentially, the dotty compiler will essentially compile out the type parameters immediately and replace them by the refinements and type members that you have seen. That keeps the foundation simple, because it turns out that if you write a type checker, then the hardest part is always feature interaction. So you have essentially many different types, and then you have operations on these types, but then how the types work together. So it's usually pretty simple to say, operation, let's say membership on this type should give you that, on this type should give you that. But then you say, well, what if it's a composition of an existential over a type projection? And it's I don't really know. So that's the main problem. So the solution, the answer to that is to say, well, let's reduce all these things into a very, very minimal core, and then we can define these concepts over the minimal core and have a much better assurance that things are correct and that we essentially don't introduce new bugs in our algorithms and so on. Dotty supports an evolution of the Scala programming language. First, we are sort of working, I think we have snapshot releases now, so we're working on a developer preview. And so currently the state of dotty is that it's targeted at contributors and experimenters. So I don't really want to propose you use this as a next language for your application yet. But if you want to get involved and say, well, this is cool stuff, I want to see what, want to have a faster moving platform where new things can be implemented very quickly because we don't have 500,000 users yet, then dotty might be for you. Technical data is, so it's a new compiler. It's about a bit more than half the size of the current Scala compiler, so about 45,000 lines of code. It's currently about twice faster, so this is very welcome. So it's a much faster compiler, and I think that should improve significantly in the future, because right now we have a lot of instrumentation code there that we know slows things down, because right now essentially debuggability is much more important than raw speed, but I think we can improve that significantly in the future. The architecture is, you see on this diagram here. So essentially we have the Scala sources that can now go into the two different front-end compilers. So here's the old one, or the current one, NSC. NSC stands for New Scala Compiler, but it's really the old Scala compiler. And it essentially it takes your sources, it type checks them, it produces an AST, which is called abstract syntax tree. Then it does some transforms, quite a few of them, about 20. That gives you finally an AST, a tree that looks pretty much like a Java program. And then you go into a code generator called GenBcode, which uses GenASM, a standard code generation framework for Java bytecodes, and produces class files. And there's essentially a pickled format for essentially separate compilation, which doesn't really have a name. We just say it's a pickled, this serialized symbol tables, which you need to do if your compiler wants to essentially make sense of the program in another compilation unit that doesn't get compiled as source with it. In the dotty frontend, it's pretty much the same architecture, only we have a much richer format called tasty, typed abstract syntax trees. So essentially that allows us to essentially do whole program optimizations, because we can see the other code in detail, not just the signatures of the functions, but everything. And so tasty is essentially typed ASTs, so the ASTs you see here, and then everything gets translated into tasty. Then we have the dotty transformations, which are a lot more, about 60. So we essentially have a lot finer faces, but we bunch them. So essentially a lot of these faces get fused into a single traversal. So overall the transformations are much faster, because you have to go through the tree much less often, and that's part of the reason why the dotty is currently faster than Scala C. And then afterwards we go into the same Gen B code backend as current Scala C. So interop works by essentially the fact that the dotty compiler can also read the pickled information from the Scala C compiler. But in the reverse currently that does not work. So essentially you have to cross-build to make it work for both things. The Scala NSC compiler cannot make sense yet of tasty, the intermediate format of dotty. So that's the compiler architecture. What we want to use that for, in part, essentially, is to say, well, can we write a compiler that sort of is more understandable, is smaller, is faster? So that's, of course, worthy by itself. But also, in part, it is to have a good basis for language evolution, for evolving the language. And here, my goal has always been and is still to make Scala the best programming language I know how to make. Of course, there's no agreement what is best, so different people have different tastes and requirements. So all we can really do is try to find a local optimum. So to say, well, if what you're after is in this space, then that solution is clearly better than the other. But we can't really say a programming language that's best for all possible use cases. Finding that local optimum is what drives me these days. So the essential elements, so essentially the space where Scala is, where what we can play with, I believe is a language that has both functions and classes and objects, that has strict evaluation. So I don't think we have laziness as an option, but I think the default mode is clearly strict. That has local type inference, so Hindley-Milner is out, and that has implicits. And currently, many languages are moving in that space, whether you say Swift or C# or Kotlin or many, many others essentially are migrating towards that core. Definitely for the first four, functions, classes, objects, strictness, local type inference is sort of on the list for all of these. Implicits, not yet so much, but I expect once OCaml has adopted implicits, they have a proposal out there and it probably will be implemented soon, the floodgates will open and everybody will want them, or at least that's, one can dream, right? Okay, so the goals I have for the evolution is first to deepen the synthesis of functional programming and modular programming. Improve the connection of Scala with its theoretical foundations, improve the guarantees of the type system, and at the same time stay simple and approachable. So essentially, we want to bring out what makes Scala special, and that I believe is this combination of functional and modular object-oriented programming. That's sort of the core of it, and we want to sort of, what my aim always was to say, well, let's try to make this sort of as good as we can instead of trying to emulate something else. And Scala is a great language to emulate lots of other DSLs and things like that, but shouldn't be its only purpose. I think the purpose should be to actually work on the core. So what I want to give you is essentially a whirlwind tour of dotty, so where we currently are, what's in store, and there's going to be a lot of material, so if some of it goes a little bit fast, then approach me afterwards and I can give you more details. So first, we don't really want to have a huge language. In fact, small is beautiful. So before we start adding stuff, let's see what we can drop. So these are things that are dropped or about to be dropped. First thing is procedure syntax. So that's, I think, a thing I believe everybody agrees on. So this sort of special syntax here of the run method that you see up here, that's really, it's not really, doesn't gain you a lot, and it gives you an awkward choice, should I use one or the other. So in the future, you'll always use the thing that's at the bottom. So you always use an explicit unit because, hey, we're functional programmers, right? We don't have many unit-producing functions anyway in our program because all they can do is side effects, right? So, of course, doing so manually would be very tedious because, I mean, even though we're functional programmers, there are a lot of these instances in existing code. So There will be a rewrite tool, a migration tool that will do that automatically for the source codes. And the rewrite tool will also take care of a lot of the other transitions that I'm going to talk about. Next thing is delayed init. I think that was another thing that probably didn't carry its weight too much. The big thing here, next thing is macros. So the current version of macros will be dropped. That version, to tell the truth, has been labeled experimental ever since its inception, for 5 years. So I think it's about the longest running experiment in language design, and it's an experiment we're going to discontinue. And I realize that that's probably going to be a problem for a lot of people, but just wait, hold your breath, and in a couple of slides we will present an alternative. Early initial, oops, what happens now? Okay, coming back. Okay, early initializers. Who knows what early initializers are? Good. For those of you who don't know, which is the absolute majority, that's what they are. So that's the syntax. So let me just explain it to you before we remove them. So essentially you... So essentially we can have a class C, and it can, before it extends any class, we can essentially have definitions here, like this Valix. So what does it mean? So what it meant was that if you do that, so normally if you have definitions here, they will be initialized after the superclass will be initialized. And sometimes that's inconvenient. So sometimes you want things to be initialized before you have the superclass initializer. And that's what the early initializers did. That said, it was a kind of a weird feature. Most of you don't even know it exists. And we now have something which I believe is much more conventional and better and simpler to use, and that's just trait parameters. So you can pass parameters to traits. And when you do that, they also will essentially be evaluated before the trait gets initialized. So you have the same initialization order with a much more conventional and standard syntax, and of course trait parameters are useful for lots of other reasons as well. Existential types are these things that I believe that if you go to complicated existential types, like things like that, then it's probably a code smell, and you probably soon after you probably see that your type checker will give you weird errors that you don't really fully understand and things like that. So it's probably much better to actually say, well, that probably was a feature that is too fragile and in general not a good idea. The simple existential types that we can express with wildcards will still remain supported, because I think that's absolutely essential, but sort of the over your top complicated thing where you have complicated for some clauses will be dropped. General type projection, so I talked about that already in the dot context. So the hash, where on the left-hand side of the hash you can have an arbitrarily complicated type, was shown to be unsound in the dot context. So the only thing we're going to keep is projection from classes. So if that T is a class C, then that essentially models an inner class in Java, so we have to keep it in order to be able to talk about inner classes, and it also turns out that this special use case is perfectly sound, so we can keep it. Okay, so that's sort of all we shed. So what do we propose to add instead? So the first thing is intersection and union types. So intersection is essentially just a small syntactic variation on the with thing here. So instead of T with you, you now write T and you. And now, of course, the rewriting tool will take care to do that for you. So why use an and instead of a with? Well, the and has a different semantics, a different meaning, and it has much nicer algebraic laws. So in particular, the and, the new intersection types, are commutative. So T and you is the same thing as you and T, which is very nice, which was emphatically not the case for T with you. T with you and you with T were two different types that resolve differently, because they essentially underwent the linearization of class inheritance where you use the with. So, and linearization means, well, order matters, so it's not commutative. So that was a big thing which in the end also makes code cleaner and simpler. So I believe it's a big simplification to go from compound types with width to intersections. Once you have intersection, the dual of that would be union types. So union types are written T or U, and that essentially gives you an untagged union of two types. So you can write, for instance, string or number, and that's a type that's either a string or a number. It doesn't have a tag like left or right or things like that, but you can always find out what it is with a pattern match. If X is a string, if X is a number, then you can do that. The main reason for having unions was, well, it's a nice dual of intersections, okay, but the main practical reason is that with unions we can avoid exploding labs. So probably a lot of you have already seen amusing examples of error messages that span dozens or maybe even hundreds of pages of code because you have absolutely humongous types. Maybe some of you have experienced them in practice already. So that was also always the problem, that to compute the upper bound of two types, let's say you have an if then else, and you need to say, well, if in the if branch I have T, in the else branch I have a U. And I say, well, what's the type of the whole thing? Well, it must be sort of the least upper bound of the T and the U. With T or U, you have a concise way to write that. That's what the type is. Without it, you have to essentially compute it differently with the types that's there. The spec is quite clear. It has to be the least upper bound of those two types. The problem is that that least upper bound can sometimes be infinitely large even, or very, very, very large. And that's essentially these exploding labs that you have seen, which in practice are very, very annoying and also don't really make for a faster compiler if it has to compute types like that. So the OR types should help here. Function arity adaptation, that's sort of a minor annoyance, but I think it will help a lot. So what we would like to write, and what I guess a lot of us already wrote, is let's say you have a list of pairs and you want to map a function like that, just sum the two parts of the pairs. Can't do that because that's a function that takes two arguments, and what you have is a list of pairs, and a pair is just one thing, right? So the trick that I guess a lot of us have learned is that you write it like this. You say pairs map, and then you say case xy, x plus y. So you just put a case in front of the thing. And that's a cute trick, and it helps a lot, but we shouldn't have to think about these things. So that's probably a thing that the compiler should be able to take care of. So function adaptation, function arity adaptation does that. So that's another thing that we have in here. Trait parameters, I already mentioned them. So we can now pass value parameters to traits as we can to classes. Static methods and fields. So there's a static annotation that makes, and you can only use it in an object, but it means that the implementation of this val and this def will be a true static method in the Java sense, not just a member method of the object. The main reason for having this is really Java interop, because quite a few Java frameworks just demand that it's a static, not an instance field of a record. So it's useful to be able to write that in a general context. Lazy vals, so there's some improvements in store for lazy vals, and I think some of them will already come in 2.13. The first thing is that lazy vals now have this problem that they lock the object during the evaluation of the lazy val, and this locking can, in the worst case, lead to deadlocks. So we have a revised scheme that essentially uses much shorter locking, so essentially it's essentially lock-free. There are just two locked periods which are of bounded length. They're just a couple of instructions each, and the rest of these things wouldn't use locking anymore. So that should essentially remove and avoid all the problems with lazy vals and deadlocks. The other thing we want to do now, not in 2.13, but only in dotty once we have the rewrite tool, is to make the default behavior of lazy vals to be thread local. So right now, the deadlocks and essentially the whole thing with lazy vals meant that in order to access a lazy val, you have to go through a fairly complicated and costly locking protocol, because different threads could access the same lazy val. And that leads can lead to problems. So essentially it means that everybody pays the price of having lazy vals because a few applications want to access lazy vals from different contexts, from different thread contexts. So what we want to do is essentially flip the default and say, well, if something should be thread safe, then mark it with volatile, like you would do for all strict values if you want them to be safely published, and use lazy vals only for thread local things. So that's essentially one thing we want to do. And again, a rewriting tool will help, of course, because it can add these volatiles for you automatically. And the next thing is multiversal equality. That's essentially a way to get type safe equals and not equals. So in the future, when you compare two things that are incomparable, like let's say a string and a number, the compiler will tell you that you can't do that. We have a compiler warning now that does these things, but that warning is pretty leaky. So it only works for some types and some combinations, and it lets a lot of other things go through. With multiversal equality, we give you essentially the power in the libraries to do that for your own types. So essentially you can define in the library what types are comparable to what other types, and the compiler will essentially give you an error if you do different things. The design of that was very subtle because, again, we want to be backwards compatible. So it means that if now you compare an any to something else, then it could be equal. So multiversal equality also has to let you do that. So a lot of the other proposals of the triple equals, essentially the ones you see, are in a sense stricter because they don't have to have this backwards compatibility requirement that you say you still need to be able to essentially compare everything with everything, but if it's obviously stupid, then you should be told by the compiler. And finally, there are named parameters. So that means for method parameters, we have the name parameter syntax, right? So named and default parameters, and they're quite useful. So the question is, why not do that for type parameters? And obviously it would be useful as well. First, if you write map key equals int, it's probably quite legible to say, well, I mean the key parameter and not the value parameter. Maybe to be forgotten in what order they come. So it helps legibility. And furthermore, it also helps you to leave these parameters out. So here, I have only specified the key parameter, not the value parameter, which will mean that the value parameter will be inferred. So the compiler will say, well, the key is explicit, the value is inferred because you haven't given them explicitly. Okay, so the motivation for all these was a better, closer to the foundations, better contact with the foundations, make them easier and safer to use, and more orthogonal. The improvements in detail are in the type system. So essentially we revamped the type system. It's now strongly influenced by dot. And there's a much better integration of type refinements, which are essentially the basis of everything now. The type inference got also revamped. So where before it was relatively ad hoc, now we have a pretty systematic way to map types into constraints. And then to solve these constraints, so constraints are typically subtype constraints, and we have a subtype constraint solver to take care of type inference. That hopefully should make type inference much simpler to specify than has been the case so far. So it's another goal to actually get to a point where we can specify exactly what type inference, not just type checking, but what type inference does. For the implicit search, we have a faster search algorithm which is better behaved for contravariant types, and for value classes we now support both nested value classes and in the very near future arrays of value classes. So value classes should be much more usable and performant than they were before. So who's working on all this? So far the main contributors are from EPFL, Dimitri Petrashko, who's going to talk about some of the optimizer work on the compiler later, Guillaume Matres, Vladimir Nikolaev, Felix Mulder, and the Scala team at Lightbend also helps with very good discussions, infrastructure reviews and suggestions, and very much is in the loop of all this development. And it's a community project, so if you want to get your hands dirty, very welcome, and let's talk after the talk. There's some tooling. Tooling is still pretty rudimentary, but some of the things are already there. So we have SPT integration, so you can launch a dotty project from SPT. We have a REPL, and it even has syntax highlighting. We have on the IDEs, that's not that much yet, but JetBrains is working on an IntelliJ plugin. We have a prototype for a dotty doc, so essentially a Java doc, a Scala doc adapted to the compiler, and we have this whole program analyzer and optimizer called the linker, which uses tasty for serialization, and that should make specialization and a lot of other optimizations much cheaper and more robust, and Dimitri will talk more about that later in the conference. So I just want to spend a couple of words on essentially what are the more far out things that we are on the horizon here. So what you've seen so far is essentially things that are implemented. So we have them in dotty, you can try them out. I'm not saying it's production quality yet, but it's there. So these are things that are not yet implemented, but that we hopefully will have in the near future and midterm future. Just got stuck on, okay. So the first thing and very important thing I realized for the future releases is Scala Meta. So I said macros were experimental, they're essentially too much tied into with the existing compiler. They expose a lot of compiler internals that should have been hidden. Eugene has been working on for some time now on the Scala Meta project, which should be a much more principled approach to meta programming and macros. In particular, instead of exposing a lot of compiler internals, you work mostly with quasi-quotes, so it should be a higher level of abstraction, but you should still be able to do the essential things that you did, at least with sane macros. So the proposed syntax for that is actually to split it, to have essentially an inline modifier for the function inlining, so you can use that for your regular function as well. It will just guarantee that they will be inlined, and then that inlining could already do a lot of things, a lot of program optimization things if you want to, but if you then want to inspect the code, like do a pattern match over your trees using a quasi-quote, then you would do it in a meta block. So essentially inside meta, you can actually see the things that are in your environment as trees, but if something is an inline, like an inline parameter, then that would be a compile time constant, so the meta block would see it as an int and not as an expression tree of int. So the reason for the change is it hopefully is much simpler, there are fewer implementation dependencies, and it should also be safer because we should be able to sandbox this thing much better. Then next thing on the horizon is implicit function types. So this looks like a pretty smallish feature. So what it is that that's a function type, and we let you write implicit in front of it. So that's like an implicit method, takes an implicit parameter, but it's a function type. So it means it's a type of a value. You can have this type as a part of another type, and you can compose these things. So what it means is that if you then declare a function, let's say, which is of this CTXS, context XS, then you can write implicitly context, and it will pick up the context from that type. So essentially, if you write it that way, then that gives you the implicit parameter, but the implicit parameter is now part of your return type. And on the other hand, if you write f of e, so you apply the function, then you also need to find the context, and as usual for implicits, the compiler will find it for you. So why the change? It's actually, it looks very small, but it's really huge because it's the first time that we can abstract over implicits. Abstract means you have a concept, you name it, and afterwards you use just the name instead of writing out the code all the time. So here, for the first time, you can actually say this thing is implicitly parameterized, give it a name, use the name, instead of repeating that same implicit over and over again in all your code. So it gives you a lot of reduction in boilerplate, it gives you a lot of increase in safety, because what if you forgot the implicit somewhere, then maybe it would be picked up somewhere else. Now you can put it in a box and be sure it's there. And it eliminates a lot of boilerplate. So once you give people abstraction, they can do anything. So once you give people abstraction over implicits, I believe there is a lot of things to be gained. The next thing is even further out, but at least as exciting, and that's an effect system. So effect checking is, of course, very much in demand. I think we all have a sort of Haskell envy to say, well, Haskell is pure, and we would so much like to be pure, but we can't, or at least the language doesn't enforce it, and we don't really have a good essentially type checker that tells us we're pure unless we essentially have put in a lot of conventions, go over a lot of monads, and so on. So I think we can do a lot of better than monads to achieve effect checking, and actually as you might have noticed by now, I'm very fond of implicit parameters, not implicit conversions, but implicit parameters, and I think they are a natural fit. So the idea is that essentially an implicit, instead of saying you have an effect, like you throw an exception, you say, well, I need the capability to throw an exception. And you get that capability with an implicit parameter. And you essentially don't need to write the implicit parameter because we have implicit functions. So that's essentially the gist of it. On the function types, it means that we will have two function types, the pure ones, which are written with a single arrow, and the impure ones. So if you ever wondered why Scala didn't use the single arrow for functions like Haskell and ML does, now you have the answer. We wanted to reserve it all along for pure functions. Okay, once we have effects and union types, it actually turns out that we can model nullability in a very, very cheap and natural way. So that's another thing that we're thinking of. The idea is to say, well, that's another embarrassment of Scala, right? So a lot of languages now have essentially explicit treatment of nulls, so non-nullable types. And Scala is sort of one of the last languages that holds out and say we are impure, every type can have null. So the idea is to get rid of that and say, well, types don't have null by default. So if you want a default, then null by default, then you add a question mark to the end of the type. So print stream question mark would be essentially the type that's a print stream or null. And what the question mark really means is just a syntactic abbreviation for saying, well, it's the type or null. So it's a union type of the type or null, which is essentially a type that has a null as the single object. Okay, now you can say, well, I can do that, but it would mean that I have to write system.out as print stream question mark. And then how do I write print on? Because obviously, once you have types that are nullable, then you shouldn't essentially be allowed to just refer to them as if they were not null. So that's where things get awkward usually. But the beautiful thing is with an effect system, you can actually delay that moment where you sort of get the embarrassment until very, very far away. Because you can say, well, we let you write print on, but essentially what it means is that your program will now be able to raise a null pointer exception because the out thing can be null, and raising a null pointer exception is an effect. So your program will now have an effect, and essentially with the effect checking, if you declare, you can declare it as that in a very, very lightweight manner. But in the future, at some point, you will probably want to declare it that say, well, my program has a null pointer exception effect. The beauty is you can do that once at the top of your program and say, well, I have impure code. There could be lots of null pointer exceptions and I can't be bothered to rewrite this thing. You declare it as a top to say, I have the effect of possible effect of null pointer exceptions, and the compiler is fine with it. So these implicit capabilities give you a much more flexible way to explain the effects than you would, than what the alternatives like monads could give you here. Okay, generic programming, the idea here is to get rid of these famous 22 things, right? Tuple 22, product 22, function 22 will be history. So there will be essentially, tuples will be age lists, so essentially equivalent to age lists, but will be implemented more efficiently, so in a flat representation like they are now. And the other thing it should give us is should give us much better support for ADTs. So what we want to do is essentially take a lot of the good ideas of shapeless and put the core in the language to actually make them available in a more performant and natural way. The last thing is better records where the idea as well, essentially it's also shapeless inspired to say, well, if you have tuples, we also want to have records with labels, and they should be implementable by hash maps, and they should also be something that integrates well with essentially databases, Spark, things where currently the limitations of tuples become very painful. Okay, good. So that was sort of the blue sky future. But I guess maybe a lot of you say, well, that's not really my main concern. My main concern with Scala is how do I not fall off the road? What about guardrails? So the issue here is that I think Scala's premise from the start was we trust developers to do the right thing. We're very optimistic, very idealistic in that way. But what if they don't? And what if we cannot even agree what the right thing is? And I think that's challenges that a lot of teams are facing now, to say, what is the right way to code Scala? How do we avoid abuses? Because the language is very, very flexible and very permissive in a way, so you can write all sorts of Scala code, and you might not like the Scala code that you see from a library that you see, or maybe from your teammates. So my first advice here would be read this. Everybody read this, every team read this, and follow it. So that's from Lee Howie's blog. He has a lot of very good articles in the blog, but that was one of the first ones, Strategic Scala Style Principle of Least Power. So the idea is a well-known principle, and it says we should take always the least powerful tool that does a given job. So for instance, if I want to staple papers, I use a stapler. I don't use a power drill, right? In the physical world, that would be completely obvious. Of course, I don't use a power drill. Why? Well, it would be too expensive, it would take too long, and I might do a lot of damage doing that. In programming, somehow we don't think about that. We say, well, let's just throw the most heavy abstractions to the simplest problems. And let's make things as general as possible because we might need it later. Yeah, we probably won't need it later. And the problem in doing that is that somebody who approaches your code, your API, your library, they won't know essentially what it does. The more powerful tools you have in the library, the least transparent is what it does. So the important thing here is to say if you take the least powerful tool, then essentially you get the least astonishment of the readers of your code as well. You say, yeah, well, of course, there's nothing fancy the library does because it's just written as a plain object. There's no parameterization, there's no instantiation, there's no reflection, there's no meta-programming. It's just a dumb object. So that means you won't have the surprise that it does something that you wouldn't expect that it did, and that by itself is very, very valuable. So read this. The second problem is containment. So even if our code base uses that principle of least power, we do not know whether the libraries that we depend on do the same. So for God forbid, but a library could do something like that. Implicit def I2S X and convert it into a string. Maybe inspired by JavaScript because somebody thought that was a cool idea to do these things. And actually you might laugh, but patterns like this are more common in practice than you'd like to think. So instead of least power here, you get maximal surprise. And the problem is this could right now be in any library that you use. It could lurk anywhere. And you could accidentally import that with like a wildcard import. You could get it in your code, and suddenly your code converts ints to strings. So how do you guard against that? So a modest proposal would be to say, well, if you have an implicit conversion from A to B, then you should require that either the conversion is defined in the package where A is defined, well, then presumably they know what they do, or in the package where B is defined, or the conversion is itself hidden in a package. Then again, I say, well, if you want to do dirt, then do it, but at least it doesn't leak out of your package. So that's sort of the rules. So it has to be essentially the conversions. You can't have a third package that says, I convert from A to B, like from string to int, and I'm public for everyone to see. That should be an error, at least a style error. We have to define what these style errors are. The second thing is probably also something that a lot of people have come across, and I found myself a lot of times dithering because, well, should I write xs.mapf or xs space map space f? Maybe just a quick poll, who here uses dot syntax for things like that? Who here uses space syntax? Okay, a little bit more than in New York, but I'm very glad that the majority of you still uses dot syntax. I used space syntax for a long time, and now I'm coming to regret it because I think it's just, essentially, it gives me too much choice in picking one or the other. So, because there are a lot of concerns. So here you might say, well, this looks kind of neat, but what about this? So that is clearly structured. That is much less structured, in particular if the F gets longer, then suddenly you get long sentences where you don't know what the subject and what the verb is anymore. On the other hand, what about this and that? So I think here I definitely would prefer that syntax because the min is, in a sense, an operator, and it's commutative, and it just doesn't make sense to have a syntax that sort of emphasizes the left argument over the right one. It's commutative, both arguments are treated the same way. So you see there's a difficult trade-off, and for a while I've come up sort of with an ironclad rule when to write what, and found this cannot be a language-imposed rules. So the proposal would be to, I think that's sort of taken an idea from what that was also, it's also in Kotlin, to add an annotation infix that indicates that an operator is supposed to be used infix. So if I want to say min should be used infix, I put it in the definition side. And then I should make it a style error if an operator is used in the wrong mode. So x min f, y would be okay, but xs map f would give you a warning. So that way, at least we get essentially more uniformity over code bases. The designer of a library decides how these things should be used, infix or operator, and then essentially the users of the library would have to follow that or get these style errors. Once we're there, then we can address essentially another thing which has been a big issue in Scala, an issue that's actually receding. I think we have much less disagreement about symbolic operators now than we had 2 or 3 years ago. So the question is essentially what methods, when to use operator names for methods. And I think a lot of us went through this phase of exuberance where we said, symbolic operators are cool, they make code so precise, so concise, and then afterwards we've come to regret it because enough people told us, what is this weird twiddle thing here? I don't even know how to pronounce it. So the idea here would be that to say, well, if you write a symbolic operator, what you also should do is essentially, it's an operator, use infix, and then essentially give it a legible name as an argument to this annotation. So we could require that. So to say, well, if I write plus equals, that's a well-known operator, then in the future you also have to explain what it is and write append. And I would challenge the Scala Z library to come up with essentially legible names for all their operators. But I think it's good because it would at least help this argument how to pronounce things, right? So at least we have to pronounce things, so we should agree how to pronounce them, of course. So, and of course, if you want to just pronounce them X, Y, Z or AX13, then that's up to you. But then that's essentially as a language designer and compiler writer, you can't really force people to use good names, but you can give them the hooks that sort of encourage them to do that. So as a conclusion, I think what we are seeing is that the developer world as a whole is moving to Scala, or more specifically, the space Scala occupies. So functional, strict, pragmatic is very much sort of the ordre du jour. It's very much sort of the trend where a lot of languages are going. And what we want to make sure, and I personally want to make sure, is that Scala remains state of the art. Not because I care that much that Scala needs to be super popular and needs to be on top, but because I think there are a lot of exciting new developments in the language space and in the programming space and programming method space, and Scala is a great foundation to implement these things. So we should essentially take advantage of that foundation and do great stuff. At the same time, I also agree that evolution is a scary thing and we have to manage it carefully, so that will be the challenge that we're facing over the next years. Thank you.